we have a complex number z such that the argument of this particular complex number is represented by theta. Then if we take the argument of the complex conjugate of the complex number z, that is also equals to negative times the argument of the actual complex number or the original complex number z. So let's begin with the proof. So here we will consider our complex number z to be given by, let's say it's r times cosine of theta plus I times sine theta. So what we're doing, we're considering the polar form of the complex number. So let's label this as equation number 1. Now we know that when we take the magnitude of the complex number, that's equals to z, and it's also given that the argument of this particular complex number z, so that's theta. So this is known and this is argument is given. Now fine. Now if we take the complex conjugate of the complex number z, all we have to do is replace the value of the iota with negative iota. That means our polar form of the complex number as represented in 1 will simply becomes multiplied to sine theta minus I times sine theta. Right. Now we can rewrite this particular cosine theta minus I sine theta using some properties of trigonometry. So here we can represent cosine theta as cosine of negative theta and plus I times sine of negative theta. So here we are using the fact that if we have cosine of negative theta, so this is always positive cosine theta, and if we have sine of negative theta, so that's equals to negative sine theta. What we have done is replace the negative sine theta with positive sine of negative theta, and since we know that cosine of negative theta is positive, so we replace cosine of theta with cosine of negative theta. This now means that if we take the argument of this particular complex number, which is, let's consider this to be number 2, if or simply this, so if we take the argument of the complex number 2, which is actually argument of the complex conjugate of the complex number z, that's actually equals to, so we'll have negative theta. Right. Now we have already obtained that positive theta is given by argument of the complex number z, so that means in place of theta, what we can do, we can replace it with argument of z. So hence we have successfully shown that when we take the argument of the complex conjugate of the complex number z, that becomes equals to negative times argument of the original complex number z. Hence proved. So here we have two complex numbers z1 and z2 with argument given by argument of z1 is theta 1 and argument of z2 is theta 2. Then if we take the argument of the product of the two complex number, that simply equals to the sum of their individual argument. So let's begin. So we will start with each of our given complex number. So we'll consider our given complex number in its polar form. So we have z1, which will be equals to, we'll consider r1 multiplied to cosine of the argument of the complex number z1, that's theta 1. So here we have cosine of theta 1 plus the imaginary number iota multiplied to sine of theta 1. So let this be equation number 1. And we'll also consider the second complex number z2. So this will be also represented in the polar form as r2 times cosine of the argument of z2, which is theta 2, plus I times sine theta 2. We are going to label this as equation number 2. Now let's begin by multiplying the complex number z1 with z2. So this will be equals to, we will simply take the product between r1 and r2. We will multiply cosine of theta 1 plus I times sine of theta 1. This will get multiplied to cosine of theta 2 plus I times sine theta 2. Right. So we'll need to distribute cosine of theta 1 plus I sine theta 1 with cosine of theta 2 plus I sine theta 2. So let's begin. So here we have r1 times r2. So here cosine theta 1 times cosine theta 2 plus I times cosine theta 1 times sine theta 2 plus I times sine theta 1 times cosine theta 2 plus I squared times sine theta 1 times sine theta 2. So this will be equals to R1 times R2. So we will combine the first term and the last term, because here we have I squared and we know that square of iota, so that simply equals to negative 1. So that means our fourth term becomes negative sine theta 1 times this is actually sine, let me rewrite it. This is sine theta 1 times sine theta 2. Yeah, so this will be negative sine theta 1 times sine theta 2. So let's rewrite it. So we will have cosine of theta 1 times cosine of theta 2 minus sine theta 1 times sine theta 2. From the second term and the third term, we can take iota as the common factor. So this will get multiplied to cosine theta 1 times sine theta 2 plus sine theta 1 times cosine theta 2. Right. Now, we have a standard form. So this is actually is the expansion of cosine theta 1 plus theta 2. Whenever we have cosine theta 1 plus theta 2, so its expansion will be cosine of theta 1 times cosine of theta 2 minus sine theta 1 times sine theta 2. This will be added to I time, and this is the expansion of sine theta 1 plus theta 2. Fine. So that means we have obtained our product of the two complex numbers z1 and z2, that's equals to r1 times r2, and this particular form. Now if we take the argument of our product of z1 and z2, so this is actually given by theta 1 plus theta 2, because that will be the argument. And what is theta 1? When we have already been provided in the problem, the theta 1 is actually argument of z1 and theta 2 is argument of z2. So this is the argument of complex number z1 plus theta 2 is the argument of complex number z2. So hence we have successfully shown that whenever we have argument of the product of two complex numbers z1 and z2, that simply equals to the sum of their arguments. So we have two complex numbers z1 and z2, and it's given that the argument of complex number z1 is theta 1 and argument of complex number z2 is theta 2. Then if we take the argument of complex number z1 when the complex conjugate of complex number z2, so that's given by argument of z1 minus argument of z2. Now before beginning, we are going to consider two results that we have already proved in the previous two problems. That means if we have argument of the complex conjugate of a given complex number z, so that's simply equals to negative times argument of the complex number z. So this is the first result that we will use. So let's label this as number 1. And the second result being if we have argument of the product of two complex numbers z1 and z2, so this will be simply equals to the sum of the arguments of complex number z1 and complex number z2. So let's use this. So in our case, we'll start from the left hand side. So here we have argument of the complex number, the product of the two complex numbers z1 and the complex conjugate of z2. So if we use proper result number 2, that means this will be simply equals to argument of z1 plus argument of z2, and this bar meaning it's the complex conjugate of z2. Now for the second term, we are going to use the result number 1, and this means this will be simply argument of z1. Since we have argument of the complex conjugate of z2, this will be equals to negative times argument of complex number z2, and this is a right hand side. So we have successfully showed that the argument of the product of the complex number z1 and its the conjugate of z2, that's given by argument of z1 minus argument of z2, hence proved. Here we have two complex numbers z1 and z2, and the argument is given by theta 1 and theta 2 respectively. Then we need to show that argument of the quotient of the two complex number, that is z1 divided by z2, that simply equals to argument of z1 minus argument of z2. So let's begin with the proof. So what we'll do, we will start by considering our given complex numbers z1 and z2 in its polar form. So let's represent z1 as r1 times cosine of, since its argument is theta 1. So we have cosine of theta 1 plus iota times sine theta 1. Right. Let this be equation number 1. And we will consider our complex number z2, which is given by r2 multiplied to cosine of theta 2, since its argument is theta 2, plus iota times sine theta 2. We'll label this as equation number 2. Right. So let's begin by considering our complex number z1 and divide it with z2. So that means we have r1. This will be multiplied to cosine of theta 1 plus iota times sine theta 1. Whole thing divided by z2, which is r2 multiplied to cosine of theta 2 plus I times sine theta 2. Now our goal will be to represent z1 over z2 in its standard form. That means in the a plus ib format. For that, we'll multiply both numerator and denominator with the complex conjugate of cosine theta 2 plus I sine theta 2. So the complex conjugate is simply given by cosine of theta 2 minus I times sine theta 2. We'll multiply that to the numerator as well. So we have cosine of theta 2 minus I times sine theta 2. Right. Now what we'll do? We'll multiply the numerator and the denominator. So let's begin. So in the numerator, all we have to do is multiply this particular expression with this particular expression. So that means we will have cosine of theta 1 times cosine of theta 2 plus I times sine theta 1 times cosine of theta 2 minus I times we have sine theta 2 times cosine theta 1 and negative iota squared times sine theta 1 times sine theta 2. Fine. So this is the numerator part and whole divided by the denominator. So in the denominator we have r2 times, so here we have cosine theta 2 plus I sin theta 2 and it's multiplied to its conjugate. So this will be simply multiplied to, or will get multiplied to. So we'll have cosine squared theta 2 minus iota times sine theta 2 whole square. Right. So what we'll do? We are going to combine the first term and the fourth term, and since iota squared, we know that iota squared is simply -1, so this will become, the fourth term will become positive. And we will combine it with the first term to get r1 multiplied to, so we have cosine of theta 1 times cosine of theta 2 plus sine theta 1 times sine theta 2 plus iota times, so we'll combine the second term and the third term. We are going to take iota as the common factor, so this will get multiplied to sine theta 1 times cosine theta 2 minus sine theta 2 times cosine theta 1. Whole thing divided by r2 multiplied to cosine squared theta 2 minus iota squared sine squared theta 2. Now what we can do here, if we consider our numerator, so here we have cosine theta 1 times cosine theta 2 plus sine theta 1 times sine theta 2. Actually, that's the expansion of cosine of theta 1 minus theta 2. So whenever we expand cosine of theta 1 minus theta 2, we'll get this particular expression. Plus iota times, and this expression sine theta 1 times cosine theta 2 minus sine theta 2 times cosine theta 1, that is the expansion of sine of theta 1 minus theta 2. Right. Whole thing divided by r2. Now here we have cosine squared theta 2. So since iota square is -1, so that means this entire expression now becomes cosine squared theta 2 plus sine squared theta 2. Now that's an identity with a value of 1. So that means in the denominator we have r2 multiplied to unity. So that means we have obtained the complex number z1 divided by z2. So that's given by r1 divided by r2. Whole thing will be multiplied to cosine of theta 1 minus theta 2 plus iota times sine of theta 1 minus theta 2. So what we'll do, we'll take the argument of this new complex number z1 divided by z2. So argument of z1 over z2. So this will be actually, so here r1 over r2, that is actually some constant. So let's say r1 over r2, we can represent it with r. So if we do that, so this does not come into effect here. We only need the argument of z1 over z2. So this will be theta 1 minus theta 2. Now in our problem, we are also provided with the value of theta 1 and theta 2. So here we're given that theta 1 is the argument of complex number z1 and theta 2 is the argument of complex number z2. Meaning we have argument of complex number z1 minus argument of complex number z2. So this is the argument. So whenever we have argument of the quotient of two complex number z1 over z2, so that simply equals to argument of z1 minus argument of z2. So hence we have successfully shown the following result. So we have two complex numbers z1 and z2 and the argument is given by theta 1 and theta 2 respectively. We need to show that the sum of the complex numbers z1 and z2, if we take its absolute value and square it, this is given by these two expressions. So let's begin with our proof. So what we'll do, we will begin by considering our given complex number in its polar form. That means we will consider our complex number z1 to be equals to r1 times cosine of theta 1 plus iota times sine of theta 1. We're going to label this as equation number 1. Then our second complex number z2, so this will be equals to r2 times cosine of theta 2 plus iota times sine theta 2. So we're going to label this as number 2. Right. Now let's find out few things. First, we'll obtain the absolute value of our complex number z1. So that will be equals to, all we have to do is take the square root, and inside the square root we'll have r1 times cosine theta 1 whole square. So this will get added to r1 times sine theta 1 whole square, which will be equals to, we have square root of r1 squared, so this will get multiplied to cosine of theta 1 plus sine of cosine squared theta 1 plus sine squared theta 1. Or r1 square root of r1 squared, that will be simply equals to r1, which will be multiplied to square root of cosine squared theta 1 plus sine squared theta 1. And we know that this is an identity with a value of 1, so we have r1 multiplied to square root of 1, so this is simply going to give us r1. In a similar fashion, we can show that the absolute value of our complex number z2, that will be equals to r2. We're going to label this as number 3 and number 4. Right. Now what we'll do, we will now add our complex number z1 and z2. So let's start by adding complex number z1 to z2. This will be equals to, so here we have r1 times cosine of theta 1 plus iota times r1 times sine theta 1. So this will get added to our complex number z2, which is r2 times cosine of theta 2 plus iota times r2 times sine theta 2. Fine. So what we'll do, we will combine the like terms together. So that means we'll have to combine the first term and the third term. So this will be r1 times cosine of theta 1 plus r2 times cosine of theta 2. This will be our real part. This will get added to the imaginary part, which is the second term and the fourth term. So we'll take iota as the common factor. So iota get multiplied to r1 times sine theta 1 plus r2 times sine theta 2. Fine. So this is our complex number z1 plus z2. In the next step, we're going to take the absolute value of z1 plus z2. So this will be equals to square root of, so underneath the square root we have the real part, which is r1 times cosine theta 1 plus r2 times cosine theta 2. We will square it, plus we'll take the imaginary part. We have r1 times sine theta 1 added to r2 times sine theta 2, and we will also square it. And in the next step, what we'll do, we'll get rid of the square root by squaring both sides. So we have absolute value of z1 plus z2 whole square. Now let's square and add the terms, the combined terms within the square root. We don't have to use the square root now. So this will be r1 squared times cosine squared theta 1 plus r2 squared times cosine squared theta 2 plus 2 times r1 times r2 times cosine of theta 1 times cosine of theta 2. Then we square this particular expression. So this will be r1 squared times sine squared theta 1 plus r2 squared times sine squared theta 2 plus 2 times r1 times r2 times sine theta 1 times sine theta 2. Now what we can do, we can combine this particular expression and this particular expression by taking r1 squared as the common factor. So this will get multiplied to cosine squared theta 1 plus sine squared theta 1. Then we'll consider this particular expression and this one and add them. So here we have r2 squared as the common factor. This will get multiplied to cosine squared theta 2 plus sine squared theta 2. Then we'll finally combine this particular expression and this expression. So we'll have 2 times r1 times r2. So this is the common factor. This will get multiplied to cosine theta 1 times cosine theta 2 plus sine theta 1 times sine theta 2. Fine. So this will be equals to, so we have r1 squared. This is an identity, the standard identity with a value of 1. So we simply have r1 squared. Similarly for the second term, cosine squared theta 2 plus sine squared theta 2 is also 1. So this will be r2 squared plus 2 times r1 times r2. So we have cosine theta 1 times cosine theta 2 plus sine theta 1 times sine theta 2. This entire expression is actually the expansion of cosine of theta 1 minus theta 2. And finally what we can do, we can replace r1 squared with absolute value of z1 squared. We have already obtained in equation 3 and 4. Plus absolute value of z2 squared plus 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So this is the value of absolute value of z1 plus z2 squared. So we have obtained the first part. So we have successfully shown that this expression holds true. Now we'll go to the second part. Now in the second part, what we'll do, we will consider equation number. So let's write out equation number 1. So that's z1 equals to r1 times cosine of theta 1 plus iota times sine theta 1. And we have our complex number z2, but we'll consider its conjugate. So this will be equals to r2 times cosine of theta 2 minus, so instead of positive iota we have negative iota, times sine theta 2. What we'll do, we'll multiply the two complex numbers z1 and the conjugate of z2. So this will be equals to r1 times r2. So we have cosine of theta 1 plus iota times sine theta 1. That will get multiplied to cosine of theta 2 minus iota times sine theta 2. Now this we were going to distribute it. That's a very simple distribution. So let's write it down. We will have, now we know that iota squared is equals to negative 1. So that means negative iota squared will be equals to positive 1. So we can replace this with positive 1 and combine it with the first term. So that means we now have r1 times r2 whole multiplied to cosine of theta 1 times cosine of theta 2 added to sine of theta 1 times sine of theta 2 plus iota times sine theta 1 times cosine of theta 2 minus cosine of theta 1 times sine of theta 2. Fine. Now this gives us, so we have r1 times r2. This is the expansion of cosine of theta 1 minus theta 2 plus iota times, and this particular expression is the expansion of sine theta 1 minus theta 2. So that means we now have a complex number z1 times z2 conjugate, that's equals to r1 times r2 multiplied to cosine of theta 1 minus theta 2 plus iota times r1 times r2 times sine of theta 1 minus theta 2. What we'll do, we'll only consider the real part. So this is the real part and this is our imaginary part. So what we'll do, we'll consider only the real part. So we have real part of z1 times z2 bar. So that will be equals to r1 times r2 times cosine of theta 1 minus theta 2. We can replace the value of r1 with absolute value of z1 and r2 with absolute value of z2. So this will get multiplied to cosine of theta 1 minus theta 2. So this is the value of real part of the product of the two complex numbers z1 and z2 conjugate. This is done because we already obtained that the absolute value of z1 plus z2 squared. So this came out to be absolute value of z1 squared plus absolute value of z2 squared plus 2 times z1 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So in place of z1, absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2, this entire expression can be replaced with the real part of z1 times z2 conjugate. So we have z1 squared plus z2 squared plus 2 times the real part of z1 times z2 conjugate. So hence we have successfully shown that the absolute value of z1 plus z2 squared, so this is given by these two expressions. So this next proof, I am leaving it as an exercise for you to try. That this is exactly the same as the previous one, except for the fact that in place of a positive sign we have a negative sign here. So that means this positive sign will get replaced with a negative sign in each of the two expressions. So this is fine. So now what we'll do, we can use this particular proof and we can also use the previous what we already obtained. That means now what we'll try to do, we will take the absolute value of z1 plus z2 squared and we will add it to absolute value of z1 plus z1 minus z2 squared, and we will see that this is going to give us the value 2 times absolute value of z1 squared plus 2 times absolute value of z2 squared. Now we know that the absolute value of a complex number always gives us the real part. So that means this value is real and this value is real, and this is going to give us a real value. Now in the next part of the proof, we have the same two complex numbers z1 and z2. So here we have to show that if the absolute value of the sum of two complex numbers is equals to the absolute value of the difference of the two complex numbers, then it means that the argument of complex number z1 minus argument of the complex number z2, this value is given by pi over 2. So let's begin. Okay, so we have already obtained the absolute value of z1 plus z2 squared. So this value came out to be equals to absolute value of z1 squared plus absolute value of z2 squared plus 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. And we also obtained an absolute value of z1 minus z2 whole squared. So this is equals to absolute value of z1 squared plus absolute value of z2 squared minus 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So this was what we have already shown just now. Now what we'll do, we'll start with this particular expression. So here we are given the equation. Actually this is given that absolute value of z1 plus z2, this is equals to absolute value of z1 minus z2. Now what we can do, we can square both sides. So we have absolute value of z1 plus z2 whole squared. So this will be equals to absolute value of z1 minus z2 squared. So if we equate both sides, so this will be common to both of the two sides, so they will get cancelled out, and on the left hand side we will have 2 times absolute value of z1 times absolute value of z2 multiplied to cosine of theta 1 minus theta 2. And on the right hand side we have 2 times, we'll have actually negative 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. We can transpose the term on the right hand side to the left hand side and combine it to get 4 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. This will be equals to 0. So here 4 and absolute value of z1 and absolute value of z2, this will not go to 0 because we have already defined the two complex numbers. They are non-zero complex number, and 4 being a number, so that means we are left with the value cosine of theta 1 minus theta 2. So this is equals to 0. So if we know that this is true when theta 1 minus theta 2 is pi over 2 radians. In this case, the cosine value goes to 0. And we are already provided with theta 1. So theta 1 is the argument of the complex number z1 minus theta 2, which is argument of our complex number z2. So this value will be equals to pi over 2. Hence, we have successfully shown that argument of z1 minus argument of z2, this will be equals to pi over 2 whenever we have absolute value of the sum of two complex number is exactly equals to the absolute value of the difference of the two complex numbers. This time we have to show that argument of z1 is equals to argument of z2 whenever the absolute value of the sum of the two complex numbers z1 and z2 is equals to absolute value of z1 plus absolute value of z2. So we'll start with this given equation. So here we have absolute value of z1 plus z2. That's equals to absolute value of z1 plus absolute value of z2. What we'll do, we'll square both sides. Now on squaring, what we get, this we have already obtained. This was absolute value of z1 squared plus absolute value of z2 squared plus 2 times absolute value of z1 multiplied to absolute value of z2 times cosine of theta 1 minus theta 2. So this will be equals to, so here we'll take the square on both square to get absolute value of z1 squared plus absolute value of z2 squared added to 2 times absolute value of z1 times absolute value of z2. So this means we now have this term and this term will get cancelled out, so we're left with 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So this is equals to 2 times absolute value of z1 times absolute value of z2, or simply put, we have cosine of theta 1 minus theta 2 equals to 1. So this is true whenever theta 1 minus theta 2 is 0 radians. In that case, cosine of theta 1 minus theta 2 goes to 1, which implies that theta 1 is equals to theta 2. And we're already given to the value of theta 1 and theta 2, which is argument of our complex number z1. So this is equals to argument of our complex number z2 whenever we have this particular equation that's given to us. So here we have to show that if we have absolute value of the sum of the two complex numbers squared, that will be, if that is equals to absolute value of z1 squared plus z2 squared, then the ratio of the two complex numbers z1 over z2 is a purely imaginary number. So let's try to show that. So we'll start with a given equation. So here we have absolute value of z1 plus z2 squared. So this is given to be equals to absolute value of z1 squared plus absolute value of z2 squared. So here if we use the expansion of z1 plus z2, the absolute value squared, so this came out to be absolute value of z1 squared plus absolute value of z2 squared plus 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So this is given as equals to absolute value of z1 squared plus absolute value of z2 squared. Now here we can cancel out absolute value of z1 squared and absolute value of z2 squared from both sides, and this is going to give us 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2 equals to 0, or simply put, cosine of theta 1 minus theta 2 equals to 0. So this means that theta 1 minus theta 2 must be equals to pi over 2 radians. Now, we have already discussed about division of complex number. So when we had z1 divided by z2, so this came out to be equals to r1 over r2. So this was multiplied to cosine of theta 1 minus theta 2 plus iota times sine theta 1 minus theta 2. Now we just now found out that theta 1 minus theta 2 is pi over 2. So when we substitute this value into our argument, so the argument of cosine will be cosine of pi over 2 plus iota times sine of pi over 2. Now we know that cosine of pi over 2, this value goes to 0, and sine pi over 2 this goes to 1. This leaves us with a final value r1 over r2 multiplied to 0 plus iota, or simply iota times r1 over r2. So r1 over r2, this is just a number, so this number is multiplied to the imaginary number iota, so that means this is a purely imaginary number. So whenever we are dividing a complex number by the complex number, the result that we obtain is purely imaginary, meaning there will be no real part. We have two complex numbers, z1 and z2, and the argument of each of the complex number are given as theta 1 and theta 2 respectively. Then the absolute value of the sum of the two complex number, this is less than or equals to the absolute value of z1 plus absolute value of z2. So let's begin. Now, in order to prove this particular relation, we begin by considering this we have already proved in the previous section, which is absolute value of z1 plus z2 whole squared. So this was obtained as absolute value of z1 squared plus absolute value of z2 squared plus 2 times absolute value of z1 times absolute value of z2 multiplied to the sine of theta 1 minus theta 2. So we are going to label this as equation number 1. Now we know that the cosine function has it's less than or equals to 1. That's the maximum value of a cosine function is positive 1. Now what we'll do, we're going to multiply both sides with 2 times absolute value of z1 multiplied to absolute value of z2 times cosine of theta 1 minus theta 2. So this will become less than or equals to the 2 times absolute value of z1 times absolute value of z2. Now since 2 absolute value of z1 and absolute value of z2, all of them are positive, so the sign of the inequality does not get affected. Furthermore, what we'll do, we're going to add absolute value of z1 squared plus absolute value of z2 squared to both sides. That means we have 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So this will be less than or equals to, we have absolute value of z1 squared plus absolute value of z2 squared plus 2 times absolute value of z1 times absolute value of z2. Right. This, from equation number 1, the expression on the left hand side can be also expressed as absolute value of z1 plus z2, and we square it. This was going to be less than, so this is simply absolute value of z1 plus absolute value of z2 whole square. Now what we can do, we can get rid of the square root. So that means we are going to consider the positive value such that absolute value of z1 plus z2, so this is going to be less than or equals to absolute value of z1 plus absolute value of z2, and so we have successfully shown this particular inequality. So this time we have the triangular inequality, absolute value of z1 minus z2, this is less than or equals to absolute value of z1 plus absolute value of z2. So let's begin. We'll proceed this time by considering the absolute value of z1 minus z2 whole squared. So we obtain this value as absolute value of z1 squared plus absolute value of z2 squared minus 2 times absolute value of z1 times absolute value of z2 multiplied to cosine of theta 1 minus theta 2. So we'll keep it aside. Let's label this as equation number 1. Now we're going to use the fact we know that the cosine function, cosine of theta 1 minus theta 2. So this is going to lie between -1 and +1. So we will consider the situation that cosine of theta 1 minus theta 2, so this is greater than or equals to -1. Now we're going to multiply both sides of this inequality with -2 times absolute value of z1. We're doing this because we need a -2 absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. But since we are multiplying with a negative number, we have to be careful here. The sign of the inequality is going to flip, or it's going to change. It will become less than or equals to, we have -2 times, so here we have a -1, so this will become positive, so we'll +2 times absolute value of z1 times absolute value of z2. Fine. Now what we'll do, we are going to add both sides with absolute value of z1 squared plus absolute value of z2 squared minus 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So this is going to be less than or equals to absolute value of z1 squared plus absolute value of z2 squared plus 2 times absolute value of z1 times absolute value of z2. Now the expression on the left hand side can be replaced with, as given in equation number 1, with absolute value of z1 minus z2 squared. So this means we will now have absolute value of z1 minus z2 whole squared. Now this is going to be less than or equals to, and this particular expression can be also expressed as absolute value of z1 plus absolute value of z2 whole squared. Now we're going to take this positive square root on both sides, so we'll have absolute value of z1 minus z2. So this is going to be less than or equals to absolute value of z1 plus absolute value of z2. Hence we have shown this second triangular inequality as well. So we have two complex numbers z1 and z2, and their arguments are also provided. Then we have to show the third triangular inequality, that the absolute value of the difference of complex numbers z1 and z2 that's greater than or equals to the difference of the absolute value of each complex number. Fine. So let's start with our proof. So we will begin by considering absolute value of z1 minus z2 whole squared. So this was given by absolute value of z1 squared plus absolute value of z2 squared minus 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So we're going to label this as equation number 1. So here we're going to use the fact that cosine of theta 1 minus theta 2, this value is less than or equals to +1. So what we're going to do, we're going to multiply both sides with -1. So that makes us negative cosine of theta 1 minus theta 2. Now since we are multiplying with a negative number on both sides, so we'll have to flip the sign of the inequality, so this will become greater than or equals to -1. Now what we'll do, we'll multiply on both sides with +2 times absolute value of z1 times absolute value of z2, multiply to cosine of theta 1 minus theta 2, and similarly on the right hand side we have -2 times absolute value of z1 times absolute value of z2. Then we are going to add absolute value of z1 squared plus absolute value of z2 squared on both sides. We have minus 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So this will be greater than or equals to absolute value of z1 squared plus absolute value of z2 squared minus 2 times absolute value of z1 times absolute value of z2. Fine. So from equation number 1, the expression on the left hand side can be expressed as absolute value of z1 minus z2 whole squared. This will be greater than or equals to, and the expression on the right side will be absolute value of z1 minus absolute value of z2 whole squared. Now we can take the positive square root on both sides, and this is going to give us absolute value of z1 minus z2. So this is greater than or equals to absolute value of z1 minus absolute value of z2. So we will prove the fourth triangular inequality. That means the absolute value of z1 plus z2, this is greater than or equals to absolute value of the complex number z1 minus absolute value of the complex number z2. So let's begin. Now we will consider the fact that absolute value of z1 plus z2 whole squared. So this is given by absolute value of z1 squared plus absolute value of z2 squared plus 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. We're going to label this as equation number 1. Now we will use the fact that cosine of theta 1 minus theta 2, so this value is always greater than or equals to negative 1. Now what we'll do, we're going to multiply both sides of this inequality with 2 times absolute value of z1 times absolute value of z2 times cosine of theta 1 minus theta 2. So this was going to be greater than or equals to negative 2 times absolute value of z1 times absolute value of z2. Now we will add absolute value of z1 squared plus absolute value of z2 squared on both sides of the inequality. So on the right hand side also we have absolute value of z1 squared plus absolute value of z2 squared. Now using equation number 1, the expression on the left hand side, this can be expressed as absolute value of z1 plus z2 whole squared. So this is going to be greater than or equals to, and this particular expression can be expressed as absolute value of z1 minus absolute value of z2 whole squared. Right, now what we can do, we can take the positive square root on both sides, and this gives us the final inequality absolute value of z1 plus z2. This is greater than or equals to absolute value of z1 minus absolute value of z2. Hence